So we talked about conductivity. We said to conduct electricity in solution, you need charges that are not stuck together but that can separate. So that when I put my wire that's connected to a battery or the outlet or whatever, and I want a charge to be conducted or flowing through the entire wire, I need to have the opposite charges be able to move in opposite direction. And if I only have a few charges, then I can only conduct so much before I run out of charges that can freely flow in that solution. And if I only have a couple, and I put my electrodes in here that are connected to a battery or an outlet or whatever, if I only have a couple negatives in solution, then they will flow over here and stick to this positively charged electrode. And the negatively charged electrode will attract the positive ions and they will stick to it. Once I don't have any more ions in solution because they're all attracted to the electrodes, then I don't have the ability to conduct electricity anymore. So I have a greater conductivity if I have more ions dissolved to start with. So question 9 on the practice exam asks you to rank conductivity of various solutions. What you're looking for is which solution has more charges. If I have a +2, that conducts twice the electricity as a +1 because it's twice the quantity of charge that can flow through solution and get to that negative ion. So we have to analyze for each one of these how many total charges there are in solution per unit volume of solution. Right? It's really, if I have a certain volume of solution, it's the more charges I have in that volume, the more electricity I can conduct. So the first one is 0.100 molar calcium chloride. The second one is 0.120 molar NaOH. Then I've got 0.050 molar AlCl3 and 0.250 molar CSI. So in this example, you can't just look at the initial molarity and say whichever number is higher will have a greater conductivity, because that's moles of compound per liter of solution. What I need to know to make a true comparison is moles of charge per liter of solution. And some of these compounds have more charge per unit than others. So what we need to do is to look at what will the charges be once this compound is dissolved. And when I have a metal and a non-metal, they should separate when I dissolve that into their individual ions. And I can predict what the charges and how many charges there will be based on separating those ions, making sure I recognize that they have the charge they need to make a noble gas configuration and for this original substance to be neutral. When the NaOH separates, I'll get an Na plus and an OH minus. The oxygen and the hydrogen won't separate. They're held by a covalent bond. Only the ionic bonds will separate when I dissolve substance, unless it's acting as an acid or base. But we don't have that here. We just have charged particles separating, and I've got to keep these reactions balanced. Oops. Because I'm trying to figure out how many total charges will be present once it dissolves. So in the first one, if I start with 0.100 mole per liter, or molarity of the calcium chloride, for every one of those, I get 1 calcium and 2 chlorides. So the molarity of the calcium is going to be 0.100 molarity, but the chloride is going to be 0.200 because I have twice that number because of the 2-to-1 mole ratio in the balanced equation. So this one becomes 0.100 molarity calcium ions, 0.200 molarity chloride ions, But since each calcium has two charges, that really is 0.200 molar of positive charge. And since each chloride has one charge, it's also going to be 0.200 molarity of negative charge. So these are the numbers that I'm really concerned with, and those are going to add together to a total of 0.400 molarity of charge. That's what I'm interested in. If I'm interested in conductivity, I want to know which has the most charge. So that's the quantity of charge for that solution. For the next one, I'm starting with 0.12. But in this case, when I balance it, everything's a 1-to-1 ratio. So I'll get 0.12 of the sodium and 0.12 of the hydroxide. And since each unit only has one charge, then I don't have to worry about getting more charge than I have molarity of ions. So that's going to be 0.120 molarity of positive charge and 0.120 molarity of negative charge for a total of 0.240 molarity of charge. So that solution will conduct less electricity than the first one, and it will conduct proportionally less based on the difference or the ratio of 0.4 to 0.24. Looking at the next one, this is going to be 0.050. This is going to be 0.050 molarity. For the aluminum, since I have 3 positives for every ion, I have to multiply that by 3. So I get 0.150 molarity of positive charge. And since I have 3 chloride ions for every 1 aluminum chloride, because of that, the way it's balanced, I'm going to also multiply that by 3. So I have 0.150 molarity of negative charge for a total of 0.30 molarity of charge. And in the last one, there's no coefficients or quantities of charge greater than 1. So I don't have to multiply that by anything. I just add them together to get 0.5 molarity of charge. So to rank them from most conductive to least, the most conductive is going to be the 0.250 CSI because it has the greatest quantity of charge. Then, the second would be the calcium chloride because it has 0.4 moles per liter. Next would be the aluminum chloride because it has 0.3. And then lastly, the 0.120 molar NaOH.